Okay, so today we're going to conclude the part on the web ontology language on OWL. And we're going to talk about decidability and ways to implement entailment for OWL. So the last time we spoke in the last two classes about OWL and the class before that about RDFS. So we mentioned about problems that are undecidable, that we cannot implement computer programs for. And we spoke about how the domino tiling problem is undecidable. And the domino tiling problem is essentially given a set of dominoes like this with different colors. Is there an infinite tiling such that we have compatible colors? So we have blue, blue here, red, red here, green, 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 yellow, yellow here. So adjacent colors in the tiles. So this problem is undecidable. We can reduce the halting problem to a domino tiling problem. So again, we have as input a set of dominoes, a finite set of dominoes like D. And we have as output true if there exists a valid infinite tiling like T that expands in the positive direction, tiles the positive plane, and false otherwise. Okay, so we're going to start today by looking at how we can reduce from the domino tiling problem. How we can express that as an OWL entailment problem, how we can actually model this problem as an ontology, which sounds a bit bizarre, but we can, which we'll see, which would then tell us that OWL entailment is undecidable. So we're going to reduce from an instance of this problem, does D have an infinite tiling, to does OWL ontology O entail ontology O prime? And this is based on proof by Sattler and talk by Sattler. Uli Sattler from University of Manchester. So how can we encode a domino tiling question into an OWL ontology entailment question? It seems kind of unusual that we can actually reduce from this to this. So we'll have a look and see. So there's some description logic symbols here that are mainly just for reference. I'll explain them as we go. I'm not going to go through all of them, but they're mainly on the slides for reference. And we've already seen some of them in the first class on OWL. So, okay, first of all, here's our problem. And now we have to start to define this in terms of an ontology. So we're going to use two pieces of terminology here to start with. The first is we're going to call a tile a piece, and we're going to call a domino a group of tiles of the same color. So it's sort of like the domino is the class, like of all of the tiles of the same color, and the tiles are then the instances of dominoes. And it'll just make things a little bit easier to talk about, right? So a tile is an individual piece, and a domino is a group of pieces that have the same colors. Same orientation of colors, right? So green on the top, red on the left, yellow on the bottom, blue on the right. That would be a domino, for example. So, okay. So reducing from OWL entailment to tiling, the first thing we're going to say is that there exists some things called tiles, and each tile must have a domino type. Okay, so essentially, we're just modeling this idea here where we have tiles that are instances of some domino. So we can define tiles to be a class, which will denote T, and we can define that as the union of classes for each domino type. So we define essentially the class of tiles, which is all of these pieces here, and then we define it as the union of the tiles for individual pieces. I'm admittedly slightly confused as to why there's overlap here, but okay. So I think this is, I'm not sure why, yeah, that doesn't make much sense. These should be disjoint. Okay, yeah, sorry. So at the start, we're not going to define them to be disjoint. So we're going to define T, the class of tiles, to be equivalent to the unions of all the classes of dominoes, right? So this is equivalent class here, and this is union. Or if we wanted to look at it in Turtle, it would be tile is equivalent class to the union of D1 to DK, where the D1 to DK are the dominoes that are provided to us as part of the input for the domino tiling problem. So yeah, so we define this setting here, but we still haven't defined that a tile in this case, still a tile can be an instance of more than one domino, right? So we need to now define that a tile is strictly one of like exclusive or one of these dominoes. It can only be of one domino type. So what else do we need to encode? We need to encode that each tile can only be one domino type, which gives us essentially what we're looking for here, that the classes of dominoes are disjoint. So to do that, we can encode this by either defining all domino types as pairwise disjoint, saying a tile cannot be an instance of, we cannot have an instance of two different domino types, which we can do by saying that the intersection of DI and DJ is a subclass of the empty class. This denotes here the bottom class or empty class for all pairs of dominoes. Or in OWL, in Turtle, we have this nice shortcut where we can just write OWL disjoint union of, which means that every tile is now every tile is now an instance of one of these domino types. Okay, so it somehow covers 1 and 2. We wouldn't need to define 1 anymore because this defines both 1 and 2, that each tile must have a domino type and each tile can only be one domino type. So this gives us this situation here, which is what we're looking for. So essentially it tells us that every tile must be an instance of at least one domino type. So what else do we need to encode? Well, we need to encode somehow the structure of the tiling. No, we just have these loose groups of tiles and their instances. Each one is an instance of one domino type. But we need to encode somehow the grid or the tiling that we're going to have. So we're going to start by saying that each tile must have a tile to the right and a tile above. Okay, so we're going to start to define this sort of structure here. And as we see, this is not exactly what we want yet because we have a yellow bottom tile above a blue top tile. So we still have more work to do, but this is a start, right? So how do we do this in OWL? We can do this by defining that a tile has some values from a tile for right and a tile for above. So essentially every tile has a tile to the right and a tile above. Okay. So here we use OR and A to abbreviate right and above. So we can define that a tile is a subclass of the class of things that have a tile to the right and have a tile above. Okay, so OR here refers to right and A here refers to above. Okay, so now we've defined precisely this. Each tile must have a tile to the right and a tile above. Okay, but we still see here that we have this problem that we haven't enforced that the colors match. Okay, so we haven't defined that the tiles to the right and the tiles above are compatible. So, okay, sorry, this is the representation of this definition in Turtle. So we say that T is a subclass of the intersection of has some tile to the right and some tile above. Some values from T on property or some values from T on property A. Okay, so are we there yet? Not quite. We still have a couple more things to define to encode the problem correctly. So we have to define the tiles to the right and tiles above must match color. Okay. Now there's a variety of ways we could do this. We could actually really model that each tile has a left color, a right color, a top color, a bottom color, and so forth. And then define that the colors have to be compatible. We could do it that way. But since we have a finite set of dominoes as input, we can kind of cheat, right? So what we're going to do is sort of a brute force definition of this. So how can we encode this in OWL? Okay, this looks kind of nasty. What are we saying here? essentially what we're just saying is for every domino types, we're defining that, for example, domino type 1, we're defining all of the values that it can have to the right, all of the dominoes that it can have to the right, and all of the dominoes that it can have above. Okay, so if domino 1, for example, it has the right-hand side of domino 1 is, for example, red, D1, then we're going to define that all of its right values must be all the ones that have a left side that is red. Okay, and likewise, we're going to define that, for example, if it has a blue top, then it can have above, all of the values it has above must have a blue bottom. So that's what we do here. We just, for every domino type, we define by hand all of the dominoes that it can have to the right. That would be this set here, or D1. These are all of the dominoes that D1 can have to the right. And intersect that with, then we say, and it must have all values above that are compatible with the top color of D1. So these are, again, all of the dominoes that we can have above D1. So by hand, we define this, right? So, and this is no problem because K is finite. So we can write out all these definitions. So in Turtle, it would look a little bit like this. So for every domino type, we're going to say that it's equivalent to the intersection of having all of the values from the compatible dominoes above. This is the list of dominoes that can go above Dn, and all of the dominoes that can go to the right of Dn, which is this Dn or here. So this just essentially enforces us to have compatible tiles to the right and compatible tiles above. Okay, so are we there? Well, we're pretty close. So there's one more thing. Well, we have to discuss a couple more things, but there is one issue that we still haven't discussed, which is that this forms a grid. So what we could have is somehow, what we have right now is almost like a tree. But what we haven't enforced, for example, is that the tile right and above is the same as the tile that's above and right. Okay. So here we see that this is compatible here, and this is compatible here, but we have multiple tiles that are in this position. So what we need to enforce somehow is that the tile above and right must be the same as the tile that is right and above. So how do we do that? We need to define tile right, then above is equal to tile above and then right to enforce that there's really only one tile here. So how do we do that? Well, we can define chains. We can define essentially this new relation, which is diagonal between these two tiles. So how can we encode this in OWL? We can encode it using property chains. So we can say that diagonal is like a property chain of above and right, and that diagonal is also a property chain of right and above. So essentially we define the two ways that we can get to diagonal, and then we can declare diagonal to be functional, which means that a tile can only have one diagonal tile like this. So it can only have one tile right and above, or one tile above and right. This gives us the diagonal part here. And this removes the possibility that we have two diagonal tiles, right? One above right and a different one right and above. So to define that in OWL, we say that this symbol here means followed by. So it's like a property chain. So A followed by OR is a subproperty of D, or OR followed by A is a subproperty of D. And sorry, OR followed by A is a subproperty of D, and D is functional. Okay. Or if we look at it from the turtle side, we say that D, property chain axiom above followed by right, D being diagonal, diagonal property chain axiom above right, diagonal property chain axiom right and above, and D is a functional property. So something can only have one value for D, or for diagonal. So now, okay, so we seem to have encoded a lot of details about the problem. Are we there yet? Well, we have one thing to consider, which is that we could still have a case like this where we have cyclical models, cyclic models. So we could have, something where we have right here and then right goes this way and above goes this way. So we can somehow have these sorts of models that satisfy the ontology that we've described thus far. So we haven't really defined that it expands in the positive direction. It could loop back in on itself, right? So we could try to define things such that we get rid of these cyclic models or cyclic models. And we see that these satisfy all the conditions that we defined before. So, okay, what we would also, but what we would find here is that we could remove such models by defining things to be transitive, asymmetric. It would be super useful here to avoid cycles and so forth. But essentially, it's not really necessary. Although we would need to prove it, it's not so difficult to prove that these sort of cyclic models can be expanded into an infinite tiling, right? They sort of represent a repetition that we can use to tile in an infinite way. So we don't really need to ban these sorts of models, because if there is a model like this, then it means that actually we can just sort of unfold it into an infinite tiling. So we don't need to ban or to remove or to define away these sorts of models. We can leave them. It's okay. It wouldn't be very difficult to do that, but it's somehow nice if here we have a minimal reduction. Okay, so we can just leave that be. Those models are okay. They witness an infinite tiling. Are we there yet? Yeah, we're done. We've done the reduction from tiling to owl entailment. So, okay, that's good news. We're done, but it's also bad news. Why is it bad news? Well, okay, so it means probably that this owl entailment is going to be undecidable. So there's one last thing. Okay, we're almost done. We've defined the ontology that models the domino tiling problem. Here's the ontology we've defined. And the last question is, okay, but what's the entailment question? What are we asking here? What we have to ask is, does O entail O prime? That's what we're reducing the domino tiling problem to. So here we've got an ontology, but what are we entailing here? So what should we be asking about the entailment? What should be here? And this can be very simple. This can be essentially, we can simply ask, is the set of tiles empty? Is the class of tiles empty, effectively? So again, this is the bottom class, the class that contains nothing. It's like the empty set, but the class version of that. So we ask, does there exist a tile? Can there exist a tile, right? So if there exists a tile, the thing is that that tile must have a tile to the right and above, and those tiles must have tiles to the right and above, and those tiles must be compatible and they must satisfy all these conditions here. So if there exists a tile, then there must exist a tiling, because that tile must satisfy all of the conditions of a tile that we've defined, and that forms a tiling. So if T can have any member, if there exists any tile, if it's consistent for there to exist any tile, then there is a tiling. Otherwise, no. Otherwise, the only conclusion is that the set of tiles must be empty, because if there were a single tile, then there would be a tiling. So we asked, do all of these definitions here that encode our problem, do they entail that T is empty? And here, when we talk about all of this stuff here, of course, we're going to replace D1, D2, dk minus 1 dk with the dominoes of our specific problem. And we're going to, here again, all of these Ds will be replaced with the Ds for the specific instance of the domino tiling problem that we've been given. And then we ask this here, is this class of tiles equivalent to the empty class? Okay, we could also use satisfiability, where we take all of our definitions and then we just invent an instance of a tile. We say X is of type T, right? And then we ask, is this satisfiable? Is this ontology consistent or not? So if it's satisfiable, this ontology here, we can have a model, then there exists an infinite tiling. And again, X can be any term. We can just invent something here and say, okay, X is a tile. And then we ask, is this consistent? So what this means is that since we have a reduction from the halting problem to the domino tiling problem, and from the domino tiling problem to owl entailment, then it means that owl entailment is unsatisfiable, right? Which is okay, which is interesting, but it's sort of a negative result, right? It means that there are certain entailments we cannot compute or will run forever. Of course, we could define, in this case, directly we could reduce from the halting problem directly to owl entailment, but the domino tiling reduction is quite nice, I guess, or maybe a little bit neater than what would be necessary from the halting problem. Okay. Any questions or doubts about the reduction? I think mainly the main ideas of the reduction. What I'd like you to follow are the main ways of the main ideas of the reduction. You know, following all the details is not maybe so necessary, but the overall idea that we can define something like the domino tiling problem as an owl ontology. So we can define very complex things as ontologies, and then, you know, even open problems in mathematics as ontologies, and then use owl, and we could use owl entailment to decide those problems if it were decidable, right? So, any questions or doubts? No? Okay, and this tool of reduction is a very important tool in computer science theory for proving complexity and, well, decidability of problems, right? Can we create a computer program to solve this problem? Oftentimes these will be these sorts of questions will be resolved through the use of reductions, or is a problem in P or NP. There are different types of reductions used for different types of proofs. In this case, this would just be a Turing reduction, that there is a Turing machine that can do this reduction. In other cases, we might have some restrictions on how much time, or, you know, what size this reduction results in. We might have to say that to restrict that for certain types of complexity proofs. But in this case, it's just that somehow the reduction itself is decidable, we could say. So, okay. This is not just for OWL. This doesn't mean, you know, this proof isn't just that OWL is undecidable, but there's this general idea of knowledge representation being undecidable. So this is the idea of telling machines stuff about the world in some formal way, and then asking them questions about what they can conclude about the world, right? So this idea of knowledge representation, of representing knowledge in a machine readable, machine processable format, like ontologies like we see here. Unfortunately, if we tell them too much, if we sort of use too expressive formalism, then reasoning becomes undecidable. Then a machine could potentially run forever and not give us an answer to the question we have in our knowledge representation formalism. So something similar happens, for example, for first order logic. So this is sort of disappointing. It means that machines have a limit, right, in terms of what they can reason about. So with this in mind, how do we proceed, right? So what are we supposed to do now, right? So in the lab, somehow you're using reasoners, and the reasoners give answers, but it's an undecidable problem. So what is that reasoner doing, right? They didn't just give up and go home because the problem is undecidable, but rather there's some choices we have to make. So we have three different options here, right? If we have this undecidable problem, there is, you know, possibly a fourth option, but it wouldn't be great for this particular choice. But it's, well, okay, it's similar to one of these options here. But okay, the first option is that, well, we need to choose two, right? So we can have a reasoner that always halts, okay, that accepts any ontology, and that always returns a correct response. So we can choose two, but we can never have three, because if to have three would imply that we have a complete sound and complete a correct algorithm that runs on any input and always halts, which would mean that the problem is undecidable, right? So we need to choose now two of these things here, right? So we can have a reasoner, for example, that always halts and accepts any ontology, but it might not always return the correct answer. It might miss entailments, for example, right? Or it might say that two ontologies are not entailed when they are. Okay. We could have a reasoner that accepts any ontology and the response is always correct. Okay. So this is the full entailment over any ontologies, but in some cases it might run forever, right? And we won't necessarily know in which cases it will run forever, or when it's just about to halt, right? Or we can have a reasoner that always returns a correct result and always terminates, always halts, but we would have to restrict the ontology language. We would have to say, okay, we only accept certain types of ontologies that we know to be decidable, to allow for decidable reasoning. So we have these three options amongst these choose two things. Accept incomplete reasoners that halt. So this is, we accept any ontologies. The complete language, people can use the features however they want. But we might sometimes say that something's not entailed, or we might miss entailments. Okay. That would be the most typical one, where we say false when it should be true. Saying true when it should be false is not common. But it will always halt, it will always terminate. This is sort of like a best effort. Let's get as many entailments as we can. Let's accept everything and get as many entailments as we can. The second option, it would be to accept complete reasoners that may not halt. So there are first order logic theorem provers. There are systems that can, take these sorts of definitions and just process them, right? And if it doesn't halt, it doesn't halt, So these are complete reasoners that may not halt. So they will accept the ontology. The ontology can define anything in the language. If it returns, then the answers will be complete, but it may not return. And finally, OWL, restrict OWL, so reasoning becomes decidable. So we see that for full OWL, reasoning is undecidable. So how about not defining, using all of OWL? Maybe we can just use a fragment of OWL, a part of OWL that we know to be decidable. So restricted language, we don't accept all ontologies now, only restricted ontologies. And with that, we can provide complete reasoning. So always returning the correct result that halts, that all is guaranteed to terminate at some point in time. Any questions or doubts on that part? No? Okay, so let's look at the first option, incomplete reasoners that halt. So in the labs, we were taking data, or RDF data, and our ontology, and we were using some black box reasoner to do some magic stuff, and then it would produce the entailments, and we would check that the entailments matched what we looked for in the question. And if we were happy with that, then we had our answer. So we never really spoke about what this reasoner is doing here. So what is the reasoner in the labs doing? It's accepting the first option. It's accepting that it will accept any ontology, and it will do some reasoning, but it might not be complete in some sense, but it will at least finish, right? It will halt. So this is what the reasoner is doing. So how does it do this? What is the reasoner specifically doing? So what it's doing is incomplete materialization, which means writing down all of the entailments that hold as a consequence of the data and the ontology. It's writing down all of the consequences. Well, not all of the consequences. It's writing down a bunch of them. It's writing down a lot of them, but it's not writing down all of them. Okay. So in some cases, we might miss entailments here in the output. We might expect to see more entailments. So in the case of RDFS, we looked at some rules. before, right? So we say, for example, that P has domain C. If we have P is domain C and XPY, then X is of type C. Or maybe a simpler example, if P is subproperty of Q and XPY, then we can entail that XQY. So we have these sorts of rules, these syntactic rules that we can apply over a graph recursively to generate some entailments, right? And this is how we described the reasoning in the case of RDFS. What we're doing here is the same thing, but we're just extending this idea to cover some of the stuff that we saw in OWL, right? So there is a standard set of rules for OWL, which form part of the web standard called OWL2 ORL RDF. And these are some rules that are defined in such a way that they are sort of complete in a specific way, but they're incomplete in other ways. So the nice thing about it is, you can say, I'm using this rule set, and then what you will entail will be well defined, even if it isn't exactly what you would expect according to the definitions we spoke about in the last class. The model theory will be missing some stuff. So what we're applying here in the labs is incomplete materialization using RDFS if we set the RDFS option in the reasoner, or the OWL2RL, which is rule language RDF rules, which is what happens if we select the OWL option in the reasoner. So what's in the OWL2RL RDF rules? Well, we have, first of all, some rules for equality. So for example, if we have SPO, then we can define that S is the same as S and P is the same as P and O is the same as O. So this, you might see these annoying inferences in the lab that are making it difficult to see what you're looking for, where everything is the same as itself. We have X is the same as Y is the same as X same as Y same as Z, transitivity is same as X same as Z. We have S same as S prime, SPO. Any ideas what would be entailed here? Take a drink of tea. So this would tell us that S prime is S prime PO. Right, so if these two are the same, and if here we have S, then we can replace S with S prime. Somehow the terms are interchangeable when they're the same as. P same as P prime, SP prime O, O same as O prime, SP O prime. X same as Y and different from Y. So if X is the same as Y and is different from Y, that's a contradiction, right? So we're going to use the term false, like just simply false to say, okay, there's a contradiction here. This is inconsistent. So we can detect that using rules. We have a bunch of rules as well for properties, where we define, okay, we include the rules for RDFS. So we import some rules from RDFS for domain and range. For a functional property, if P is a functional property in XPY1, XPY2, what could we conclude here? Any ideas? So if P is a functional property and we have XPY1 and XPY2. So for example, biological father, a functional property. Sam has biological father Fred. Sam has biological father Tim. Okay, maybe then we would say that Fred and Tim are the same, right? Somehow that something can only have one value for a functional property. Inverse functional property, that's the same idea, but in the other direction. P, a symmetric property. So if we have XPY, so for example, sibling a symmetric property, Fred sibling Alice, then we can infer Alice YPX, Alice sibling Fred. Transitive property, P, a transitive property. Ancestor, for example, a transitive property. If we have Fred ancestor Bob and Bob ancestor Alice, then we should have Fred ancestor Alice. So XPZ. And so forth. We have rules for property chain axiom, for equivalent class, for disjoint property with inverse of. To take another example, XP1Y, we can infer YP2X, right? So we have two rules for inverse of and so forth. So you can go through these later, but you get the idea that we have a bunch of rules for defining inferences over OWL ontologies. So for classes, okay, we have subclass, we import that from RDFS. We have equivalent class, which is sort of like a subclass, but in both ways. Disjoint width, where C1 is disjoint with C2 and X is C1 and C2, then we infer, we say that there is an inconsistency. C intersection of C1 to Cn. And if we know that Y is an instance of C1 to Cn, then we can infer here. Any ideas? So if we have C is the intersection of C1 to Cn, and if we have something that is an instance of each of these classes in the intersection, then we can infer that Y must be an instance of the intersection, right? C. So Y an instance of C. And the other way, we can say that if Y is an instance of C, here, the intersection, then it's an instance of all of the classes in the intersection. So it kind of works both ways. Union of, so here we have C, union of C1 to Cn. And if we know that Y is a Ci, and it's one of these classes here, any one of them, then we know that it must be in the union class C. Right? So we can entail here Y as C. So here we miss something already. So we miss, this is the only rule we have here for union of. So it works only in one direction. So it works if given an instance of this here, then it must be an instance of the union class. What we miss here is that if something is a member of the union class, then it must be a member of one of these classes here, at least one of these classes here. We don't have a rule for that because we would have to say YSC1 or YSC2 or YSC3, and this or we cannot represent with these rules. I'm trying to think about what. Oh, I was supposed to take a break. let me finish this and we'll take a break. Sorry, I'm after running over time. I thought it was 10:55. But math fail, 10:40, should be 10:45. So we'll take a break in 2 minutes. Apologies for that. So all values, some values from. So we have rules for some values from and all values from. Taking this example here, if we have X all values from Y on property P and UPV and UAX, then what we can entail is that, okay, what this says is X all values from Y on property P. It says that this class is the class of all things whose instances, whose values on P are all instances of Y. So if we have that U has value V on property P and U is an instance of this class, then V must be an instance of Y. Okay, so V type Y. We'll take this example here of max cardinality. So we say that we have a class that has max cardinality 1 at most one value for a property P. And then if we have something that is an instance of such a class, and if it has multiple values for P, then we don't say that this is inconsistent. Rather, we say that those values must be the same. Y1 same as Y2. So there's some rules that we skipped. We won't go through all of them. They're here as well, so you can kind of refer to them on the slides. But hopefully you get the idea that, you know, we're defining these rules that don't cover everything we could entail from these OWL features, but they cover somehow the most important stuff. And you have experience of these rules because these rules are essentially what are being used to give you the entailments that you saw in the labs. But these rules are not complete. So there's a bunch of stuff that's, okay, sorry. So there is one last type of inference that these rules provide, which are the schema rules, which allow us to have, to define entailments at or inferences at the level of schema. So for example, we can encode the transitivity of subclass, where we say if C1 is a subclass of C2 and C2 is a subclass of C3, then C1 would be a subclass of C3, right? Or if C1 is a subclass of C2 and C2 is a subclass of C1, then we can infer that C1 is equivalent class of C2, right? Or if P is a domain of C1 and C1 subclass of C2, then we can infer that P domain C2. If C is an intersection of C1 to Cn, then C1 to Cn. C would be a subclass of each of C1 to Cn. Likewise, if C is union of C1 to Cn, it goes in the other direction. C1 to Cn must be subclasses of C. So somehow it gives us some partial inferences at the level of schema, at the level of the definitions about classes and properties. Okay, so with that, we'll take a break. Apologies for getting my times mixed up until 11:05. Any questions or doubts or? So we saw the schema rules for L2 or L or DF, the rules that it defines. It's worth mentioning that these are not the complete list of rules, but these are somehow the most important rules of this type. So there's a ... here to indicate that some other rules are also defined. So we mentioned that this is incomplete reasoning, that it's not going to give us everything that we might expect. And it's missing various entailments for various features that we've conveniently not needed in the lab. Okay, so for example, if we know that something is a reflexive property, and we have something, x something or xpy or whatever we might want to say, then we should be able to entail that xpx, right? So if it's a reflexive property, then everything is related to itself by p. So p could be, for example, similar to, everything is similar to itself. We also saw this feature in the first class on L, which is has self-true. For example, if a narcissist has self-true on the property loves, which means that if something is a narcissist, U is of type X. So if something is a narcissist, then U loves you, UPU. In the other direction, if we know that UPU, then we know that if U loves itself, then we know that U is a narcissist, UAX, right? So we can entail in both directions. If X is the inverse of X, we have this sort of schema level stuff now where we can infer, for example, if X is an inverse of X, then X is a symmetric property. For example, if sibling is the inverse of sibling, then sibling is a symmetric property. If X is the inverse of Y and Y is the inverse of Z, if we think about it for a second, we might see that X and Z must then be related somehow. And in this case, they're related through being equivalent properties. They're the exact same property. If X is the inverse of Y and Y is a functional property, then X is an inverse functional property, right? So inverse functional property is like functional property in the other way. So if we combine inverse of with functional property, we get inverse functional property. If X is the complement of Y and Z, then we could entail some relation between Y and Z here. Complement of meaning that if X is the complement of Y, then everything is either in X or in Y, right? So in that case, we can entail that Y and Z would be equivalent classes, right? Because they're both equivalent to not X effectively, right? So we can continue arbitrarily here. And in fact, we could define an infinite number of rules here that would be considered missing. So obviously trying to apply an infinite number of rules would cause problems. So we essentially stop at some point and define a specific set of rules as the rules for the L2 or RL or the F standard. So the full list of rules is available in the standard here, and it describes all of the rules that one should apply to do reasoning in this way. So the reasoning is complete with respect to this rule set, but it's incomplete with respect to the model theoretic semantics that we saw, the general definitions of the meanings of the L features that we saw in the previous class. So we're going to miss some entailments, because to get everything, we would need an infinite set of rules, and that's just not possible. So in what way are these rules incomplete? So the first is that we'll look at some examples that exemplify general ways in which they're incomplete. So we saw this example in the first class that if Vincent is of type person, and person is equivalent to the disjoint union of criminal and lawful, meaning that every person is either criminal or lawful and cannot be both, then we have this sort of conclusion here that Vincent must be one of criminal or lawful, right? Which we can't represent with these rules. We can't say Vincent is criminal or Vincent is lawful. We can't represent that with these rules. So if we had this sort of ontology or definitions here, so Vincent is a person. Vincent is a godfather. Person is equivalent to the disjoint union of criminal or lawful. Every person is either criminal or lawful, and godfather is disjoint with lawful. Nobody can be a godfather and lawful at the same time. If we think about it, then we can rule out, we know since Vincent is a person that he must be either criminal or lawful. And he can't be lawful because he's a godfather, right? So what we can entail here is that Vincent is of type criminal, right? It's the only other option. We sort of rule out this option here. So the only other option that's left is that Vincent is a criminal. We won't get this entailment because we have to be able to model or understand that Vincent must be either criminal or lawful here, which we never write down. So we don't get this entailment from these rules. So these rules will miss this valid inference because it misses the information that Vincent is criminal or lawful. It doesn't consider that. It just sort of ignores that. We also miss things relating to negation. So we miss, for example, in this case here, what we could get this by saying that Vincent is not, we would also need to realize that Vincent is not lawful, right? So we don't really write down, we don't in general write down negated things we know to be not true. So we would also miss this inference for that reason. Because we don't handle negation with these rules. So we don't handle in this case that Vincent is not lawful, right? We don't write this down with these rules. And we know again, he's not lawful because he's a godfather and godfather is disjoint with lawful. So there's no way Vincent can be lawful. We could definitely infer that Vincent is not lawful. So we don't capture that with these rules. Another way these rules are incomplete is with respect to things that exist, but we don't know what they are, right? So if, for example, we say that Michael is a parent, and the parent is equivalent to having some values from person on property has child. Here we're assuming parents are people. So a parent is essentially someone who has a child that's a person. And then we define that has child is domain fertile, okay? So in this case, we know since Michael is a parent that Michael must have a child and that child must be a person. And since Michael has a child, then we should be able to entail that Michael is fertile. Unfortunately, L2, the rules again will miss this valid inference because it doesn't write down that Michael has some child. It doesn't consider this thing that exists, right? It doesn't write it down because it can't name it. So we miss this inference. And yeah, I'm awarding this the worst example of the course, but hopefully it gets across the point. So essentially, we don't consider that Michael must have some child, and therefore we don't apply the domain rule. That we don't have anything to apply the domain rule on, so we miss this inference. Okay, so it's incomplete in a number of different ways. There are certain features that are just not considered, they're not included, and why that is, I'm not actually 100% sure. There are problems with disjunction, which we saw with the criminal or lawful case. So we can't consider this sort of case A or case B. Problems with the existentials, things that we know exist, but we cannot name. There are problems with counting. If we go beyond 1 in particular or 0, if we say that something is 2 or 3 or 4, then we have no support for that. Problems with negation. This is things that are not true. We have problems with that. And incomplete schema inferences, like we saw, for example, if P is the inverse of P, then P is a symmetric property. So we have some inferences to capture some entailments, but we miss an infinite amount of these sorts of inferences. So this means that when we talk about zebroids, we spoke about ways we could define zebroids using ontologies. But if we were to apply these rules, we wouldn't infer that Zia is a zebroid based on the parents, right? So based on this example here, we said that, okay, if Zia has sire Marty and dam Leia, and Zach has sire Marty and dam Leia, the same parents, then we could infer that Zia is a zebroid, right? But we wouldn't get this inference with these rules. Why? Because there's a disjunction here. There's somehow this idea that Marty might be the horse or non-zebra equine, and Leia might be, or one of them might be the zebra. We don't know which, so there's sort of like this implicit disjunction that either Leia is the zebra or Marty is the zebra, and the other one is the non-zebra equine. And we can't really model possibilities, different possibilities like that with these rules. So we're not going to get this sort of inference with L2 or LRDF based on the definitions we saw previously, which is sad. Okay. So we can definitely do reasoning. We can get lots of useful inferences, but somehow the inferences are not going to be, they're not going to reflect the complete entailments based on the abstract semantics that we defined before. So any questions or doubts?
Yeah, so is there no way to define it at all? Like we did on the 2 classes before?
Yep, there will be, and that will be the third option. So if we were to do rules, we could of course extend our rule set to cover this particular example. So we could add more rules until this example works. But then there would be an infinite number of other examples where it doesn't work, right? It's sort of like we have to stop at some point, and we could continue, but we could continue to infinity, right? So in theory, we could define a rule set that covers these sorts of cases. But that rule set would not cover other cases, right? So there's this thing of having to stop at some point and say that this is enough. But this is the first option, which is using incomplete reasoners. And we're going to see another option that will cover that soon. So not using rules.
Thank you.
Yeah.
Thank you.
Okay. So the second option where we could get this sort of inference would be a complete reasoner that returns all of the entailments, but it may never halt. Or more specifically, when we say complete, often here we think about the entailment problem where we're not materializing, right? Because in every case, no matter what we're doing, the number of entailments can be infinite, so we can continue forever. But here what we're saying is that it will always return true or false for the entailment question. Okay, so I kind of blurred the lines a little bit there, but it's in any case, this means that we always get the correct answer for entailment, whether it's true or false, whether something's entailed or not. However, it may fail to halt in certain cases. So there's really very, very little work on this option, which is kind of a little bit confusing because I think it's a pretty practical option. I think things not halting is not the end of the world, although, people being logicians and people working in computer science theory like things to be decidable, and they like looking for decidable things. If it doesn't halt, it doesn't halt. At least then, okay, we're not sure, right? So there's only one line of work I know in this, which is using first order automated theorem proving to essentially reducing OWL entailment to first order automated theorem proving. And we see here that what it's saying is it can support the full ontology language, like everything we defined previously. It just may not halt in certain cases. So there is some work on that. And these first order automated theorem provers are often used for verification or even for helping with mathematical proofs. They can offer proof assistance that can help to somehow to find assignments that somehow resolve a proof. So, okay, what are the pros and the cons here, the advantages and disadvantages? Well, the big disadvantage here is that the reasoner may never halt, right? Might run forever. What are the advantages? Well, the advantages are that we can avoid what's coming next, which is we can avoid trying to define these complicated. So the first advantage is we have complete reasoning. And the second advantage is we can accept any ontology. And we don't have to apply all these weird restrictions on the ontologies to make sure that reasoning is decidable, which is the third option that's coming next, right? We can just accept any ontology. In some cases it'll work, some cases it'll never halt. But at least if it returns, we know that the answer is correct. So in terms of avoiding the complicated decidability restrictions, I mean, it's sort of analogous to if you were to think about restricting a programming language like C or Java or Python to be decidable, and you were to say, okay, we don't want programmers to define things that will never finish or that will never halt. So the first thing is that if you, the first option, if you were to try to restrict a programming language to make sure that the programs in that language always halted, would be to just disable a lot of features. So you could disable things like loops or recursion, right? But this would be, too coarse because, well, maybe some programs with loops or some limited forms of recursion are guaranteed to halt. These features are very useful in many cases. So it would be kind of overkill somehow it would be too much to just remove these features because you would have a much less powerful language that couldn't do half of the things it can do, right? So then maybe you could think about, okay, let's try to keep loops and recursion, but we have to be careful about, how they're used. We have to apply certain restrictions on how loops and recursion are used to make sure that our programs in this new programming language will always halt. But then we need somehow we have this trade-off, right, between this simple restriction that's too much, like it removes too much power from the language, and these very fine-grained detailed restrictions that might enable us to keep loops and recursions in certain cases. But what are those cases? It can be very complicated to define precisely what the restrictions are to make the language decidable. And in general, like in this case, maybe it's better that we just let people write whatever programs they want. And if they halt, they halt. And if they don't, they don't. Do we really need to restrict? Does it really make sense to restrict the programming language to be decidable in this sort of case? So by just saying, okay, well, we have complete reasoning, sometimes it may never halt. It's kind of like programming languages. Yeah, you can write your program. Maybe your program will never finish, but hey, that's life. So that's the second option. And the third option is to restrict OWL to guarantee decidability, which means that we're going to have complete reasoning that always halts with the correct answer, but we're not going to accept all ontologies. Rather, we're going to say, hey, all of these ontologies are now banned. They're forbidden because if you use these features in this way, the reasoning becomes undecidable. So we've seen how could we go about restricting OWL to guarantee decidability? How do we know what features we need to turn off or to restrict? So we've seen how to prove that something is undecidable, or one way to prove that it's undecidable, which would be a reduction from, for example, an undecidable problem like the halting problem or domino tiling problem to our problem. In reverse, how can we prove that something is decidable? So the easiest way in general is just to give an algorithm. So you give an algorithm, you prove that it's complete, it always gives the correct answer, and you prove that it will halt eventually, given enough time and resources. Or you can also use maybe something that's a bit less constructive. So you can use some clever argument that, that says basically that it is using some sort of abstract argument. So in general, what we have in OWL is there's been a lot of work on this description logic community, which has been very interested in decidability. So it's a community that predates OWL. It existed before OWL existed and inspired a lot of what was defined in OWL. And they've studied these sorts of decidable subsets of first order logic, these decidable ways of doing knowledge representation, of looking at what is the maximum amount of knowledge, the maximum expressivity of our knowledge representation that we can have, while still being sure that the machine will eventually be able to come up with an answer. And these results can be applied to OWL as well. So they're really interested in decidability. It's sort of like a key aspect of this community. So this gives rise to different sub-languages of OWL. The first is OWL2 full, which is you can write anything you want, unrestricted, undecidable. You can define everything that you might like with those features. OWL2DL is OWL2 description logics, is a restricted decidable version of this language with certain things disabled to ensure decidability. And then there's some other sub languages of that. But this is the key aspect here, because this language will enable decidable and complete reasoning for us. So I think we're out of time. We can continue this in the class on Wednesday. The overall thing is that on Wednesday, we're going to use a complete reasoner. We're going to use a different type of reasoner. We're going to move away from RDF Playground for one lab. And we're going to use a different type of reasoner that I'm going to explain in the last part. And this reasoner is precisely this type of reasoner. It only accepts ontologies that are valid in OWL2DL, in this restricted version of OWL, but it will return given two ontologies, it will always be able to decide whether or not the first ontology entails the second one. So it's complete in that sense, and it always holds. So we can get these more complicated types of inferences like we saw with the zebroid. Z is a zebroid, which we couldn't get with the rule-based reasoner we've used thus far. Yeah, so we'll finish this class on Wednesday. I don't think there's too much left. Just have to discuss a bit about how this third type of reasoner works. Any questions or comments? Okay. If not, see you on Wednesday. This will be the last class and the last lab on OWL. The next class we're going to move to Sparkle. So see you on Wednesday. Hope you have a good week until then.